still, remember in this chapter, we want to calculate V. We want to determine V when you are given the pressure and the temperature. Okay. So other than the cubic equation of state, we also have other equations of correlation. Okay. Okay, so next is the generalized correlation for gases. What's this picture? Generalized correlations for gases, if you refer to the textbook, it's on page 99. Okay, so we have a generalized correlation. There are two types of generalized correlation. For gas, we have the first one is what we call the pizza correlations for compressibility factor. And then the second one is still pizza correlation, okay, but the first one is using the Lee and Kessler correlation. The second one is based on the virial coefficient, second virial coefficient. Okay, so the first one, we have this general equation which correlates between Z, the compressibility factor, and then Z0 ataupun Z0 plus omega Z1. Okay. So for this one, although it is stated for gas, you can also use this equation for liquid for some condition. Yeah. Kenapa kita panggil dia generalized? Sebab as you can see later, nanti saya akan tunjuk because this Z0 dengan Z1 ni kita boleh baca daripada table dekat appendix, dekat belakang buku teks tu. Why we call it generalized? Because it doesn't depend on substance. You know, it only depends on the temperature and pressure. So if you know the pressure, you know the temperature, tak kisahlah dia methanol ke, dia butane ke, it will determine the value of Z0 and Z1 and of course Z. Okay, that's why it is called generalized. Okay, so Z0 and Z1 are functions of both TR and PR. So TR and PR, they are called reduced temperature and reduced parameter. Okay, ni saya dah tunjuk hari tu kan, TR dengan PR. Okay, so TR is equal T over TC and PR is P over PC. Okay, and then when omega is 0, then Z becomes Z0. So these are called simple fluids. Okay, so for the pizza correlation for the compressibility factor, so you can see here that the Z0 is a function of reduced temperature and reduced pressure. Okay, simple linear relation between Z and omega for given values of TR and PR. Yeah, so you ada Z kat sini and then this is omega. So this is a linear equation, linear relation. So of the pizza type correlations available, the Lee-Kessler correlation provides reliable results for gases which are non-polar or only slightly polar. So this is from, you can find the values on appendix E. So nama dia tu pizza correlation, but under the pizza correlation, we have another correlation which is the Lee-Kessler correlation. So Lee and Kessler correlation ni yang is the one that determines the value of Z0 and Z1. Okay, there are other calculation methods for Z0 and Z1, but the most common, the one that we use here is the Lee-Kessler correlation. Okay, so this graph here, figure 3.13, is the Lee-Kessler correlation for Z0. Yeah. So you nampak kat sini the y-axis is the Z0, value of Z0, and then the the x-axis is the reduced pressure. Okay. So how you can get the values is from appendix E. Yeah. If you don't have your textbook yet, you can open in e-learning. I already put appendix E, so you can open appendix E. Okay, appendix E here. Appendix E, the Lee-Kessler generalized correlation tables. Okay, so all you need is just is just the value of PR and TR. Okay, so dekat atas ni, on the top of the table, you have PR, okay, PR 0.01, 0.05 and so on. And then here is the TR. So based on your values of PR and TR, you can find you punya values of Z naught dekat sini lah. So you have to take note of the title So table E1, values of Z naught, Z0. And then table E2 is table values of Z1 with for the same range of PR and TR. Okay. Now, of course, when you calculate TR and PR, you tak akan dapat. Sometimes, most of the time you will not get exactly 0.01 kan. Maybe you dapat 0.012, 0.015, something like that. So in that case, you have to do interpolation, right? So you need to get the value, you need to calculate the value in between. Okay, later we will look at an example, and I think you know how to do interpolation kan. Okay, so depending on the values of TR and PR, you may need to do interpolation. Okay. All right. Okay. Another thing that I want you to note ataupun to understand is that if you look at the table, there are some values that are written in italic. Dia condong, tulisan dia condong Contohnya dekat atas kali ni, the first few lines, you can see that the values are written in italic. Apa maksud dia? Kalau dia dalam italic, maksud dia dalam liquid phase You can read the description on the first page of Appendix E. Okay, the numbers printed in italic type are liquid phase properties. Okay, that's why it's written here. They can be used for both gases and liquids. Tapi kebanyakannya ialah untuk gas lah. Okay, but just just take note that when you see the values in italic, then that means it's in liquid phase. Okay, so clear. Alright, so the second type of the generalized correlation is the pizza correlation for the second virial coefficient. Okay, so you have this equation for the second virial equation, Z equals 1 plus BP over RT. And then you have this correlation between P and, we rewrite P and T in terms of PC and PR. Okay, so in this case, thus Pizza and co-worker propose a second correlation which yields values for BPC over RTC. So this is the the equation that relates between this is actually equals B So BPC over RTC is actually equal B, and this is equal B naught plus omega B1. So nampak tak dia punya bentuk equation tu sama dengan Z tadi you just replace with B. So for the second virial generalized correlation, you have B equals B naught plus omega B1. Okay. Alright, so okay, untuk the generalized correlation using the second virial coefficient, number one, validity at low to moderate pressure. So samalah macam yang before you have learned before this. For the second virial, it's applicable for low pressure, low to moderate pressure. Where for reduced temperatures greater than TR approximately 3, there appears to be no limitation on the pressure. It is simple and recommended, and it is most accurate for non-polar species. Okay, so the second virial coefficients are functions of temperature only, and similarly, B naught and B1 are functions of reduced temperature only. They are well represented by the following equation. So second virial coefficient is very simple, very convenient, because the parameters B naught and B1 is a function of temperature or reduced temperature only. So tak kisahlah dia pressure dia apa, tak kisahlah dia jenis compound apa. If you are given the temperature, you can just, you can immediately calculate the parameters B naught and B1, and you get the B. Okay. Alright. For the Lee-Kessler tadi, we don't really have any like limitation berapa pressure dia kena low ke apa, tak ada. Ya. As long as you can find the values of TR and PR, and you can find the values of Z0 and Z1 from this table. Okay, so there is no like limitation macam second virial coefficient tadi. Okay. Alright. So, okay, so this figure is showing the comparison between the Lee-Kessler and the virial coefficient correlation. Yeah. So the point yang titik ni, point ni ialah when you do the calculation using Lee-Kessler, and then the lines are the virial coefficient correlation. Okay. So this dash, you can see this dash kan, dash. So region yang atas, above the dash region is where the difference between the Lee-Kessler correlation and the two virial coefficient correlation is, the difference is less than 2%, meaning that kalau you punya PR dengan TR is within this region, you can either use Lee-Kessler ataupun the second virial. But of course, normally kita nak guna second virial lah sebab calculation dia is much simpler. Okay, so kalau you punya PR dengan TR is outside this pink region, then you have to use the Lee-Kessler lah. Okay. Okay, let me repeat myself again. This graph is showing you kat mana applicability of the second virial coefficient correlation. Yeah. So basically, only within this pink ataupun peach color region ni. So if within this peach region, the difference between Lee-Kessler and the virial correlation is less than 2%, meaning that you can use the equation for the virial correlation. Kalau yang area lain-lain ni, you better use the Lee-Kessler lah. Sebab Lee-Kessler tu kita assume yang paling applicable for any pressure or any temperature. Okay. Alright, so we also have the correlation for the third virial coefficient. Okay, and tapi this one is less common. Okay, so in case you need to, you need to calculate using the third virial coefficient, you can just use this formula lah. Okay. Alright, example. Okay, example 4. Sorry, we don't have any international student in this class kan? Do we have international student? Ada tak? So it's okay if I sometimes use bahasa Melayu. Alright, so this example 4 is the same. Yeah, it's exactly the same as example 3.10. Not exactly the same lah. Example 3.10 you have until D, okay, but here you have C only, okay. Okay, so this in this example you have to use the generalized correlation, okay. So determine the molar volume of N-butane at 510 Kelvin and 25 bar by each of the following: A, ideal gas equation; B, the generalized compressibility factor correlation; and then C, the generalized virial coefficient correlation. Okay. So A, I think it's straightforward. So you just use the equation for ideal gas, which is PV equals RT. Okay, so you can determine the V. Okay, you put you just rearrange the equation. So V equals RT over P. Okay, just take note, yeah. I think for most of the questions in the textbook, you will find that the temperature is given in Kelvin or degree C. So when it's given in degree C, you just convert to Kelvin. But the pressure is, I think most of the time is given in bar instead of in Pascal, kan? So when you have the temperature in Kelvin and the pressure is in bar, so you can use the value of R as 83.15 here. You can see, yes. Yeah, so it's 83.14. You can use the temperature in Kelvin and then the pressure in bar, and then your answer, your value, the value that you get here, the unit will be in centimeter cubic per mole. Okay. So of course it's okay if you want to convert everything into SI unit. Okay, in that case for SI unit you will use R as 8.314, kan? For the SI unit. Tapi you also have to convert your pressure into SI unit, and then your answer for the V also will be in SI unit, which is meter cubic per mole. So just be careful, yeah. Just be careful when using the different units. So normally if it's in Kelvin and bar, then you just use 83.14 and then you get the answer in centimeter cubic per mole. Okay. All right. So for B, using the generalized compressibility factor correlation. So this is the compressibility factor correlation is given by the Lee-Kessler correlation, where you have the Z yang ini, Z equals Z naught plus omega Z1. Okay. So first you can calculate the TR. Okay, TR T over TC. So you get the TC from appendix B for N-butane, yeah. So you need the value for N-butane. Okay, and then PR sama lah. You get P over PC. You get the value of PC from appendix B. So you get the value for PR. So based on the PR and TR values, you need to find the range, yeah, from appendix E. So this is what I have written here. Your TR is 1.2. So you're lucky lah sebab 1.2 memang kita ada dalam appendix E tu. Okay, so you don't need to do interpolation for the TR. But for PR, you have to use the value because it's 0.659. So it's in between 0.6 and 0.8. Yeah. So first, you write down the values from the table. Okay. So in this case, this is 0.8779 and then 0.8330. So you do the interpolation for the PR. Okay. So in this case, I get the value as 0.865. So dia mesti in between. Kalau you calculate, you dapat value dia lebih rendah daripada lebih rendah daripada 0.83 ataupun dia lebih tinggi daripada 0.87, and then you know lah your calculation is wrong. So your answer here must be somewhere in between. Okay, so similarly untuk Z1 pun sama, you just write down the values, okay, untuk TR 1.2 and then PR for 0.6 and 0.8, and then you do the interpolation. Okay, so you just substitute into the equation. So in this case, you need the value for omega also. So this omega you get from appendix B. Okay, so dapat Z. Dapat Z, you can calculate V. Okay, so dapatlah jawapan dia. Alright. And for the C, using the virial coefficient correlation, it's sepatutnya kena tulis ni lah second virial coefficient correlation. Okay, so we suppose this is the second virial coefficient correlation, so we use this equation. Okay, so first we determine the B naught, B0 using the formula. So in this case, you just need the value of TR. Yeah, so tadi TR kita dah calculate kan here. So you just substitute lah 1.2. So dapatkan B0, dapatkan B1, you get this B. Okay, B hat ni. So so after you get this B and then you substitute into this equation, you get Z and you can calculate V. Okay. Ada soalan tak untuk this apa tu? Generalized correlation. Any questions for generalized correlation? So you have the Lee-Kessler and the second virial correlation coefficient. Okay. All right. So we continue. We also have generalized correlation for liquid. Okay. So the molar volume of liquid can be calculated by means of generalized cubic equation of state, even though often not in high accuracy. Lee-Kessler correlation can be used with which is suitable for the non-polar and slightly polar fluid. So saya dah tunjuk tadi in the Lee-Kessler correlation table tu, you can see that there are some values in italic. So those values in italic indicates that it's in liquid phase. So you can also use Lee-Kessler for the liquid phase. Generalized equations are available for the estimation of molar volumes of saturated liquids. The simplest equation is proposed by Racket as an example. Okay, so this is the Racket equation 3.72. So for this equation, it is specifically for saturated VSAT, so saturated volume. So you need VC, Z ataupun ZC and then the TR. So VC is critical volume, critical molar volume. ZC is the critical compressibility factor, which both you can get from Appendix B. Okay. So in this case, you just dapatkan VC, ZC daripada Appendix B and then you calculate TR. You can calculate VSAT. Okay. Okay, another type of generalized correlation is actually shown by this graph. So this one is developed by these three people, Lyderson, Greencorn and Haugen. Develop a two-parameter corresponding states correlation for estimation of liquid volumes. It provides a correlation of reduced rho R, this is rho density, as a function of reduced temperature and pressure. So by definition, the reduced density is the density over sorry, ini salah. This is supposed to be C. I thought saya dah betulkan. This is supposed to be C, critical. This is page 109. This is supposed to be C, yang ini. This is C. Okay, so PR is, rho R is rho over rho C, which is also equivalent to VC over V. Sebab density dengan dengan volume is in inverse relation kan. Okay, so you can rewrite when you have two when you know the volumes for two condition, two states, then you can write as this, V2 equals V1 times rho R1 over rho R2. Okay, so here rho C is the density at the critical point, and then the rho R, rho R1 or the rho R2, they are the reduced densities, which can be read from figure 3.16, this figure. V2 is the required volume and V1 is the known volume. Okay. All right, so how do you read this figure? Okay, so you need the information of TR, reduced pressure. So your axis here is the reduced pressure, and then you have the TR, ini kan, this line for TR, and then you have your rho R on the y-axis. So So how we read is, sebab normally kita ada you can calculate the PR and TR first kan. So based on your values of PR and TR, katalah you have, let's say just an example, your PR is 5. Okay, and then your TR is 0.7, let's say. So you need to apa tu? Let me just draw. Okay, let's say you have PR is 5, so you just follow this line. Okay, until you meet the line for TR equals, tadi saya sebut apa, 0.7 0.7. Okay, sorry, it's a bit difficult for me to write. It's supposed to be a straight line, vertical straight line. So this is the point. Okay, so you need to read on the y-axis kat sini lah, baca kat sini. Okay, so this is somewhere here, which is around probably 2.6, okay, 2.55 or 2.6. So that's the value of rho R. Okay, but if let's say you don't have, sebab TR, they are given in just, 0.3, 0.1. If let's say you have 0.75, right? So you can, you have to draw imaginary line by yourself. So you just estimate lah, somewhere here, this is 0.75 kan. So somewhere here, then you just you read the value of rho R is here, macam tu. Okay? I thought I already have some notes on the slide here, but it doesn't show. Oh, okay. It's on a different page. Yeah. Okay. All right. So just let's go through this example. I think you will understand better through this example. Okay. Example 5. Example 5. This is example trend 3.13, page 110. For ammonia at 310 Kelvin, estimate the molar volume of A, the saturated liquid, and B, the liquid at 100 bar. Okay, so for A, for saturated liquid, so V sat, so you can just straight away use the Racket equation yang tadi this one. And for this, you only need the info of temperature. That's why you're only given the temperature lah. Okay, so this is the solution. I cannot see this WebEx panel is hiding my, okay, all right. So this is the equation, Racket equation, V sat equals VC times ZC, power of this, okay? So you need to find the TR, okay? So to find TR, you need the TC, so you get TC from appendix B, okay? So you get the TR, and you just substitute. So VC is this 72.47, get from appendix B as well. Also same with ZC, you also get from appendix B. So you just substitute everything and you get VSAT, which is 28.33 centimeter cubic per mole. Okay, for the second question, V at 100 bar. So in this case, what we can do is we can use the generalized correlation yang pakai graph tadi kan. We can use that one. So you are given the pressure here. So you can calculate PR, reduced pressure. Okay, so you get the PC from appendix B. So you get PR. And then for the density, sorry. Oh yeah. So this is from equation 3.74. Oh, okay. So first you need to find the rho R from the graph, yeah. So your PR is berapa tadi PR? PR is 0.887 and TR is 0.76. Sorry, here. So your PR is somewhere here, 0.8. Okay, and then for the TR is 0.76 kan. So it's somewhere between 0.7 and 0.8. So katalah dekat sini, around here. So you just, get this line and then you read on the horizontal punya line tu. So roughly lah kita estimate around 2.38 kat sini. Okay, so that's how you get the 2.38 here. Okay, yang VC ni tadi you dapat daripada appendix B lah. Okay, so this equation is 3.74. Saya tulis dulu 3.74. This is equation 3.74. Okay, so you boleh substitute a V dekat depan. Okay, so V equals VC over rho R. So you just substitute. Okay, you get 30.45 centimeter cubic per mole. You can also find using the second equation. Sebab tadi generalized equation tu you ada dua. You have two equations actually. This is one equation. This is another equation. Okay, so if you solve using the second equation, meaning you compare between two states, yeah. In this case, we take the saturated liquid as state 1. Sebab apa kita ambil saturated liquid? Sebab you ada value di dekat atas ni. We already calculated the value for saturated volume, saturated liquid here. Okay, so we can use saturated liquid as the first value lah. Okay, in this case you can, cumanya dekat sini dalam textbook dia bagi experimental value of saturated liquid. Okay, if you are not given this experimental value, you can assume that this is the value. Okay, just in this case it is given in the textbook. Okay, just just as an example lah. If you have two states, state 1 and state 2, you can use the second equation. Okay, so in this case you need rho R1 and rho R2. So rho R1 is the rho at the density for the saturated condition. So untuk saturated condition ni, they are slightly different ya, cara baca, how you read the value. Okay, if when you have saturated condition, you need to follow this saturated liquid line, yang the dash line, yeah. So in this case, you just follow the TR, the TR line. So TR line tu tadi yang warna merah ataupun hijau ni is actually the same line. So you just trace sampai dia hujung, sampai dia cross the saturated liquid line ni. So this is the value of rho density for the saturated condition. So in this case, it is slightly lower than the one without the saturated condition. Okay, so we estimate around 2.34. Okay, so we substitute here. Okay, so you have this first condition volume, first condition rho R, and then this is your second condition rho R. So you get the second condition volume. Okay. Boleh, so this is how you use the second equation when you have two states, two condition. Condition 1, condition 2, so you can use the second equation lah. Okay. Alright. Okay, other than the generalized equation, generalized correlations, we can also use the steam tables, okay, to get the values of V, okay. So again, remember ini steam table. So steam, it means water. So you can only use for water. Untuk H2O sahaja. Okay, kalau you ada alcohol ke, you ada butane ke apa, you cannot use this table. Okay, remember this is steam table, so only for water. So the way you read it, okay, there are two types of steam table. Yeah, the first one, F1, is for saturated steam. Saturated meaning that you have that saturated condition lah. Saturated, that means you have liquid and vapor both coexist. So in that case, you only need you cuma perlu tahu satu parameter saja. Remember, kalau on the saturated line, your degree of freedom is only one. So you tahu satu parameter, the rest of the parameters you can determine. So in this case, you just need to know the temperature. Okay, so here is the temperature in degree Celsius, and then the next column is the temperature in Kelvin. Okay, and then this is the saturated pressure. Okay, so for example, you want to know the volume of saturated liquid at 10 degrees Celsius. Okay, contoh So 10 degree is here. So this is the temperature in Kelvin, and this is the saturated pressure. So this is the volume lah, saturated liquid 1, and then for the saturated vapor is here. So there are two one is for evaporation, one is for the saturated vapor. It's almost the values for the evap and the saturated vapor is almost the same, because this evaporation is actually a mixture of both. Yeah, yang ini dia just for the vapor, okay, and this one is just for the liquid. Okay, and take note here the unit, yeah, for the specific volume V, the unit is given as centimeter cubic per gram, not mole. Okay, so you have to be careful of the unit. Okay, another table is the superheated steam table. So this is F2. So apa beza dia tadi? Saturated means you have liquid and vapor. Superheated, I explained to you last time, superheated means when the temperature is above the boiling point. Okay, at the atmospheric pressure, boiling point of water is 100 degrees Celsius kan. So when you have steam at higher than 100 degrees Celsius, you use this. It's called superheated steam. Okay, so for each of the temperature, you have the temperature here you have the pressure and the temperature. So for each of the pressure, you are given the temperature. So temperature tu is actually the boiling temperature lah. So the boiling temperature at that pressure is actually also the same as the saturated temperature. Okay, just to alamak, saya tak tunjuk kat sini I should have shown you if you have the atmospheric pressure kan, P equals berapa ni? I only show you the first page of the table. When you have atmospheric pressure, which is ini when you have atmospheric pressure, which is 101.325 kilopascal, okay, 101.325 kilopascal, that is the atmospheric pressure, okay, which is equivalent to 1 bar. Then you will see that the value for T in the bracket is 100 degrees C. Okay, so that is what it means. The boiling temperature at atmospheric pressure is 100 degrees C. So that is also the saturated pressure of water at that saturated temperature of water at that pressure. Okay, so the value of temperature yang dekat sini pun, you have this temperature kan, 75, 100, 125. Dia mesti lagi tinggi daripada temperature yang dekat sini. Okay, for example, here you have 99 kan, 99. So you can see that dekat bawah 75 degrees sini kosong, tak ada value sebab that is not steam, that is not vapor yet, it's still in liquid. So for the superheated steam, it must be above the boiling temperature at that pressure. So 100 kilopascal, the boiling temperature is 99. So you only have value for 100 because it's above 99. Faham Okay. Alright, so this is just extra lah sebab saya pun selalu lupa because this subject use a lot of Greek letter, yeah. So you will see a lot of Greek letters. So it's just the pronunciation or the explanation for the Greek letters. Okay. You have seen the omega yang ini. The above is the capital letter, yeah. The lower one is the small letter. Okay, so you have seen omega, okay, rho, and then also this psi, psi, omega, large omega. Yeah, later you will see this phi or phi here. Kita akan guna. Of course, you've seen beta, kappa, and so on. Okay. Alright, so this is just an example of test question for. I think this is 2 years ago, 2 or 3 years ago. Okay. Just to show you how you may be asked for the, what kind of questions that may appear for the test. Okay. All right. So here, 10 moles of ethylene are to be compressed isothermally from their initial state, which is P equals 21.7 bar, T 25 degrees C, and V equals 1000 centimeter cubic per mole to 100 centimeter cubic per mole. Under these conditions, the behavior of the gas is well described by the van der Waals equation of state. Estimate the pressure at the final state using the van der Waals equation of state. So you are given the P1, T1, and V1, and also you are given V2. And then you also have this information, isothermal. So isothermal means constant temperature. So that means T1 equals T2 equals 25 degrees C lah. Okay. And then you are also given the information, okay, described by the van der Waals equation. So you need to use the van der Waals equation, which is this equation. Okay. So in this case, you need to determine the parameters A and B. So A, you need to have TC and PC. Same goes with B. Okay, so you just find the TC and PC, of course R, and then you substitute into the equation to get A and B, and then you can sub here. You use V1, yeah, which is 100. Okay. Sorry, this is. Yes, because the final state, so you need to use V2 lah. Okay, 100. Okay, so you get the value for P2. Okay, final state. Alright, question 2. If the final state is in saturated pressure, estimate the molar volume using the equation proposed by Racket. So this is the Racket equation, yeah. So in this case, you supposed to use this Racket equation lah. So you straight away find the values of BC and ZC from the appendix B, and then you use this TR, and then you just substitute everything, you get the answer. But actually, if you look at the question closely, at this pressure and temperature, actually, the substance must be in gas actually. So there is no way that it is in a liquid. Yeah, and the value for 1 minus TR also, it must always be positive. Yeah, so when you have 1 minus TR is negative, then it's supposed to be not liquid. Okay, so this actual question is actually a wrong question. It's an error. But anyway, during this time we just accept the answer lah. If you use this equation, then we accept the answer as correct. Okay. Alright, so basically that's all for chapter 3. Do you have any question? Sorry, sekejap,
Doctor, I have a question for the last patch.
Sekejap.
Yeah, this one, the question.
Oh, the question. Okay, sorry.
Yeah.
Share again.
So actually, I just want to ask, before, like all the example we have done before, right?
Mm.
So, the question all asks like, estimate a thing like volume or pressure, using what equation, right?
Yes.
So how should we know which one to use? Like in this case, right, the van der Waal, we use the P again, and then the previous example we use to find the Z again, and then go back to find the V again, then all that.
Oh, okay. Actually, for the van der Waals, can you see my slide? I think it's frozen.
Yeah, I think it's frozen. I can't see anything.
Can you see now?
Yeah, can.
Okay.
Can. I think.
Alright. So actually, for the van der Waals equation, you can also use the cubic equation of state yang panjang-panjang tu kan. Actually, you can also use that. It's just that it's actually this one is a simpler equation. But if you use that yang the one that you have to refer to the table tu, supposedly you can get answer juga lah. Mana tadi? The table 3.1. This one. You can of course use the van der Waals. You use the apa tu? But in this case, kejap mana tadi soalannya?
Because I have tried, so I understand that in this case it's not possible to like use the thing lah, because we don't have PR. We cannot find PR because P is missing for the data. But I have taken the answer here, the P 132.07 bar, right? I use this answer and then I recalculate back to the for the volume. I recalculate back using the equation, and then I
Okay.
calculate back the volume, and I get a different answer from 100 cm cube per mole. I get around how much I see? Oh, 142.98 cm cube per
Yeah,
mole.
if you
It's not
use
same.
the cubic equation, the one, it's okay, because that's why we call it estimation. In this chapter, if you notice, most of the question it will start with estimate, because the answer is apa tu? It's not 100% accurate. I mean, it's just an estimation. When you use the different equation, if you compare cubic equation and then you compare, if you use the Lee Kessler, of course the answer will be slightly different. So it's okay. But in this case, let's say, tapi kenapa you kena derive back? You can actually use the cubic equation for P.
No, because the problem is I derive that because I want to find a V and prove that both ways can be used, but I can't prove the same V lah.
Okay.
Because in this case, I think cubic equation cannot be used because we cannot find PR. We don't have P. The final pressure we don't have, because we are actually finding the final pressure.
Yes.
Thank you, Doctor.
Okay. Okay, so for this chapter is basically you have to it's mainly about the volume as molar volume. That's why it's called the volumetric properties. So as I explained to you earlier, kenapa kita nak we are interested in finding the volume, because normally you can measure the temperature and pressure easily, right? You have like a specific equipment ataupun device to directly measure the temperature and pressure. But for the volume, if you have liquid, of course you can measure the volume of liquid quite easily, right? But if you have gas, how can you measure the volume of gas? It's quite tricky. So that's why you need to be able to determine the volume from the information of pressure and the temperature. Okay. So Okay lah. So of course the simplest equation is the ideal gas equation, and then you have the equation of state, this one, and then you have the generalized equation. So generalized equation, you have the equation for gas and equation for liquids. So for the gas, you have the two types of generalized correlation, which is the Lee and Kessler, and the second one is the second virial coefficient. Okay, and then for the generalized correlation for the liquids, you have the first one is for the saturated vapor using the Racket equation, and then the second one is using the correlation of the densities. Yeah. Okay, so later I will give you an assignment, but normally I will combine with chapter 4. So I will give you assignment 1, which is from chapter 3 and chapter 4, and also your test 1 will also be on chapter 3 and 4. Okay. Okay, we still have time. Let's look at some example. Where is my... Or maybe you want to see past years punya question. Yeah, probably I will show you some past years question. Uh, mm, this one. Hold on. Okay, this is last year's questions. Okay, yeah, so as I mentioned to you just now, test 1 will cover chapter 3 and chapter 4. So normally question one is for chapter 3 and question 2 is for chapter 4. Yeah. Okay. All right. Okay, so let's read the question. A 44-liter tank is used to store and butane at 15 degrees Celsius and 5 bar. The tank can be filled up to 80% of its total volume. Okay, number 1, assuming that N-butane is liquid under these conditions, estimate the molar volume using the Soev-Redlich-Kwong equation of state. Okay, number 2, based on your answer in 1, determine the mass kg of N-butane that can be stored in this tank. And number 3, discuss whether N-butane is better to be stored as liquid or as gas. Yeah. Okay, so in this case, the question already gives you its liquid for number 1, and you must use the SRK equation. So you have to use the equation Z for the liquid root, the smallest root. This is the solution. Okay, so as usual, you need to find the TR, PR. Okay, so you get the TC, PC, and because we're using SRK, you also need omega. So you get this from the appendix B. Okay, and then you calculate TR, PR. And then for the... Okay, actually we want to use this equation at 3.56. This is for the liquid. This is the equation. But before that, you need to calculate the the beta and also the Q. Yeah, so that's why you need this information. Yeah, so beta equals large omega times PR over TR. Okay, so this omega you read from table 3.1. And then for Q, you have the psi, alpha, and also omega. Also, you take from the table. Okay. And for the SRK, the alpha is given by this equation. Yang ini, yang panjang. Okay, so you need to calculate the alpha, which is a function of TR and also omega. Okay, so you substitute TR and substitute omega, you get alpha lah. Okay, so dapat alpha baru you boleh calculate Q. Okay, so you calculate beta, you calculate Q, you sub into this equation. Also, you need to find epsilon and sigma from the table. Okay, so ini yang simplified after you sub the epsilon and sigma. So we solve by iteration, starting with Z0 equals beta. So for liquid root, we use the starting point as beta. Ya. Kalau a vapor, largest root, you use the starting point of 1, 0, Z0 equals 1. Okay, so solve by iteration. Kat sini saya stop sampai Z5 lah. But actually if you stop until Z4 pun, we still accept because the difference is only 0.0002 kan. So it's still okay lah. So after you get the Z, you can calculate V. Okay, so you get V 106.61 centimeter cubic per mole. Okay, number 2 and number 3 is actually is not really from this chapter lah. You have to use your knowledge, your previous knowledge from the from other classes as well lah. Okay, so you need to find the mass. Okay, this one I think you need to use the knowledge from your ITE class. Yeah, you need to convert. You need to from the from the molar mass, you need to find the mass, okay, because you have the volume. Okay, so this is the conversion. I do the calculation like this. So for the molar mass, you can actually get this molar mass also from appendix B. Okay, so you tak perlu nak nak panic lah macam mana nak kira molar mass ni kan. Molar mass ni pun ada dalam appendix B ya. Or the molecular weight. Okay, so the molar mass or the molecular weight you can find. It's the first column after the compound name. Yeah, so for this is N-butane. Okay, here. So it's 58.123. Okay, so you just ambil lah. Okay, so from the molecular weight or the molar mass, you can, you have the volume, specific volume, and then you have the tank capacity, and then here is just unit conversion. And then everything you need to times 0.8 because this is only, the capacity is 80% only. Okay, so you need to times 0.8 to get the final answer. Okay, and then for number 3, is it better to store in gas or is it better in liquid? For this question, actually, I accept both answers as long as you can give your justification. Yeah. So if you say gas state, yes, you can store in gas state, but it will need larger tank because, it has larger volume. Okay. But for gas state, the advantage of gas state is that it will need a lower pressure lah. Okay. For liquid state, you can compress, so the volume is smaller, but you will need higher pressure and it may also be dangerous lah. Okay, so both, if you answer is gas state, also can, liquid state also can, as long as you give the justification. Okay, so this is last year's question. And then for the previous year, I think it's the same question as I showed, shown in the last slide tadi. Sekejap, let me check. This one. Stop sharing. Yes, it's the same question as the one that I showed on the slide. So yeah, we can skip that. The previous 2019, yeah, 2019. Okay, this one. Okay, this is 2019. All right. Okay. Question 1. Isooctane gas is stored in a closed vessel at 1.5 bar and 500 Kelvin. Calculate the molar volume of the gas using 1. Van der Waals equation of state. 2. The Redlich-Kwong equation of state. Okay, and then B, how will the value of molar volume change if you use the Peng-Robinson equation of state rather than the Redlich-Kwong equation of state? Justify your answer. No need to show actual calculation, just give your prediction such as higher or lower value. Okay, so this is the answer scheme. Okay, right, so this one, you need to calculate using the Van der Waals and Redlich-Kwong, okay? Okay, so you can calculate the TR, PR, and then it's gas, yeah? So it's already stated here, gas. So you have to use the largest root, this equation. Okay, so you need to find the beta and Q, yeah? And for the Van der Waals, you can just take all the values from the table. Okay, this is for the Van der Waals. So you calculate beta, you calculate Q, and then you just sub into the equation and solve using iteration lah. Okay, and then we get this volume, yeah. So similarly with the Redlich-Kwong, you also need to find the alpha, the sigma, epsilon, okay, this omega, and then the psi, and then you calculate the beta and the Q, sub, and then iteration, get Z, and you get the B. Okay. Okay, just a hint here. When you use the different equation kan, if you use the ideal gas equation, it will always give you the largest value, the largest volume, ya. Sebab the Z is 1 for the ideal gas, betul tak? So your V will be the largest when you use the ideal gas equation. Okay, and then when you use the van der Waals, it will be slightly reduced. And then when you use the Redlich-Kwong, it will be further reduced. If you use the SRK, normally the SRK will give a similar answer with RK. Yeah, normally. If you use the Peng-Robinson, it will further reduce the volume. Okay, question B. So what happens if you use the Peng-Robinson? So using the Peng-Robinson equation, the molar volume value will be smaller and more accurate. This is because the PR equation considers omega, which is the eccentric factor, into the equation. Normally, it will be smaller and of course, it will be more accurate lah. Okay. Boleh Ada soalan tak untuk ini? The question I think is straightforward. This is 2019. I also have the 2017, 2018. Yang ini mana soalan dia? Where's the question? This is the solution. Sekejap Oh ini sorry, not this one. This one. This one. Okay, this is 2017, 2018. Lebih kurang lah, okay. You're given propane, okay, this temperature 4 to 3 Kelvin and pressure 70 bar. Assuming that propane is an ideal gas, determine the molar volume. And then B, using the Redlich-Kwong, estimate the molar volume of the gas. And then C, compare the answers from A and B. Using the estimation using the ideal gas equation is acceptable in this case. Justify your answer. Okay, A is easy lah. You just use the ideal gas. Okay, and then for the second one, you use the Redlich-Kwong. Sama juga macam tadi, you need to find the TR, PR, and then the beta, the Q. You sub into the equation, solve with iteration. And cumanya just if you notice for this question, the iteration gets quite long actually. Okay, and then you get the Z is 0.55. Normally when the Z is low, it's like 0.6, 0.5 macam tu. Normally the iteration will be much longer. Okay, in this case, you may go up to six iteration. Okay, once you get the Z, you can get the V. Okay, and then compare. Alright, of course the ideal gas equation will give you larger volume. In this case, is it acceptable to use the ideal gas? It is not acceptable because the pressure is high. Yeah, and you can see that there are large. The difference is large. Yeah, compared if you compare the answers from ideal gas and the radicom. Yeah, ideal gas you get 502. For the radicom you get 276. So it's quite a large difference, and it shows that you cannot assume it's ideal gas, yeah, because the pressure is high, which is 70 bar, yeah. So it's very high. Okay. Okay, so basically I have finished chapter 3. Next week we will proceed with chapter 4, yeah. Okay, no questions?
So far, no, Doctor.
Okay. Oh, by the way, I think probably you have heard about the latest academic circle, perkeliling akademik yang terbaru, which states that after the mid-sem break, after the Raya break, all the students are supposed to come back to UTM and have face-to-face class, yeah. At least for SKT lah, I think it's probably different for other faculties or school, but for SKT, as for what we have been informed, for the undergraduate course classes, we are supposed to have face-to-face class after the mid-sem break. So I would just like to know if any one of you cannot come back to UTM after the break. If you have problem, coming back to UTM, please let me know so I can make the necessary arrangement. Okay. Alright. Tak ada soalan So kalau tak ada soalan, I will stop the lecture.